we're going to be talking about the physics of Earth's surface. So, this is the lecture for this week. We're going to be talking about the theory of plate tectonics and how that theory is supported by evidence and the forces involved in that. So, what is the theory of plate tectonics? Well, plate tectonics is a theory of geology that explains how the crust of the Earth is made up of slowly moving plates of solid rock that float and move slowly along the liquid mantle. So the mantle is the next inner layer of the Earth. We know that it's liquid based on a variety of pieces of evidence, but I mean, whenever we experience any of it as magma, it comes out as liquid. So that's pretty compelling evidence. Well, um, this theory, the theory that the plates of the Earth are moving slowly along this surface of liquid, helps explain earthquakes, volcanoes, seafloors, mountain formation, and many other things in geology. So it's a comprehensive theory that explains the evidence that we have around us. All of these are examples of evidence that we use to support this theory. But before we get into it too much, it's important to understand the basics of the layers of the Earth. Well, especially the outer few layers. The outer layer is called the crust or the lithosphere. The lithosphere is just another name for the solid crust that's on the surface. Then we've got the upper mantle, which in other people call it the asthenosphere. Um, and then the inner mantle or the main mantle. All of this is liquid rock. We know that, but we'll talk more about how we know that when we talk about earthquakes. The outer core is made up of different materials than the mantle, but it's still liquid. And then the inner core is a solid, not because it's cold and cold, so hot things tend to melt, but in the center of the Earth, the pressure is so high that despite the really high temperature, it's a solid because it's just under such immense pressure. So we have some decent evidence to explain how we know this, but this is actually still an evolving theory. And as we get deeper and deeper, there are more and more questions that try to explain that we have about how these things act and why they are the way they are. We're fairly confident that this is liquid and solid, but we're not sure exactly why in some cases. So the closer we are to the surface, the more definite we are in our theory, and we know for sure that the mantle is liquid rock made of just magma, and the surface of the Earth is obviously solid. So because look around, there's rocks. That's what we're talking about. So, um, well, in physics, we're interested in the forces involved. Why would the solid rocks on the surface of an object um, stay on the surface, and why would they move? So the first force involved is the force of buoyancy. Buoyancy is the force where solids that are less dense than liquid will float to the surface of water of that liquid because of the force of buoyancy. So buoyancy is this upward force, and basically, if an object pushes a liquid out of the way, then the weight of that liquid wants to push back. So the more you push away, the more that upward force is. So if an object is light, if it's less dense than the water or the liquid around it, then it will float because the buoyancy force, the upward force, is less than the gravity force because it's a light object. But if it's a heavy object and it's high density, then the downward force, the gravity force, is going to be higher than the buoyant force, so it'll sink. Now, that a sinking object still has a buoyancy force, but that buoyant force is lower than the force of gravity. That's why it sinks. So it's important to notice. All right. The other force involved is friction. We've been talking about friction throughout the year. And we know that liquids will move because of convection. Convection is when you have a hot material coming up, it wants to rise. Hot materials are less dense than colder versions of the same material, so it wants to rise. And then the colder part of that liquid circulates downward, where it gets heated up at the bottom. So this happens when you have a cold object or a reason to lose heat on the top and a reason to gain heat on the bottom. So in the Earth's case, the inner core and outer core are really hot because they're creating heat due to radioactivity and have stored built up heat from um, eons past. Well, the liquid mantle gathers heat from the core and then circulates in these convection currents in these because the hot material wants to rise and the cold material wants to sink. Well, as it moves, it's going to pull on the lithosphere. That's friction. So if you move one object past another, then it wants to pull on that object, and that friction force is what causes our crust to move. So friction and buoyancy are the two main forces involved in plate tectonics. So far, we know that the surface of the Earth is solid, and we have evidence that so we know it's solid because look, we can look around at us and we can make observations. We can see it in person. And then we have evidence that the next layer of Earth is liquid, the mantle. That's because when things come out of the mantle, they are liquid. And when we talk about earthquakes, we'll talk about other evidence that we have that proves without a doubt that the mantle is liquid. And then we know that liquids undergo convection, which causes those liquids to circulate. And we know that that circulation would cause friction on the plates. So friction is what pushes and pulls the plates in the first place. All right, well, as they get pushed and pulled, there are different boundaries that plates will have relative to each other. So if I have two plates moving away from each other, that's what's called a divergent boundary. So divergent just means moving away from, and two plates that are moving away from each other have a divergent boundary. Well, crust is going to be created here because as they move away from each other, magma is going to well up from the center of the earth and it's going to cool because it's exposed to the elements, water, the atmosphere, space, and it's going to cool down and then turn into rock. So crust is created at divergent boundaries. And we can see evidence of divergent boundaries all around us. One example is the Red Sea. Well, Egypt and Sudan, Africa, the continent of Africa, are moving away from each other and away from Saudi Arabia and the Asian plate. So as they move apart, well, the new crust is formed, but it's thin when it's formed. So there's going to be a lower altitude area there, and water rushes in to fill that center. So that's what the Red Sea is. Um, Before the water comes rushing in, if you have plates diverging on land, well, you're gonna get these rifts, these valleys, where land is moving apart from itself. This is actually a picture from a textbook in 2005 where they're showing how Iceland in the two parts of Iceland are moving away from each other. I've actually been to Iceland, and after I saw this, I went back and looked at my pictures, and I have a picture from almost the exact same location. So this is a picture from my phone. You can see it's the same path with people on it. There were more people on the day that I was there, and more clouds, so you can't see the mountains as well. But this location has this rift valley. It's forming as we speak. So eventually, Iceland will split up into two islands as they move apart from each other. It'll take millions of years, though, so you've got time. Um, Once the ocean has rushed in, well, this is what the floor of an ocean will look like. So that Red Sea in the center, it's going to have these the spreading centers with active volcanoes as magma wells up and escapes, cools down, turns into rock. Well, as you get further and further away, the crust gets thicker and colder because it cools over time, and the volcanoes start to go extinct. The further away you get older, colder, and thicker, denser crust. Um, this is the so these are formed because you've got this convection, the center of a convection current with high heat flow at this location. So they're pushed apart, and a bunch of heat is welling up from the center of the Earth. So this is what it looks like. Well, the reason this is higher than this part is because this is lighter than this part. So the buoyant force is going to push it higher. It's just all this happening there. So the very center of oceans are actually more shallow than the middle part, um, like between the center and the edges. So just random. Um, the other option is for plates to be moving toward each other. So if two plates are moving toward each other, um, wait, the opposite of moving away from each other is moving toward each other. Yeah, these are called convergent boundaries. Convergent just means converging, or converging on each other means coming toward each other. Well, when the thing that happens when they run into each other, two plates crashing into each other, is going to depend on how heavy each one of those plates are. But regardless of how heavy they are, crust is always going to be destroyed here. So crust is created at divergent boundaries and it's destroyed at convergent boundaries. Well, these are the three options. So you could have different types of crust. Continental crust has thicker, denser crust at the bottom, but then it has a thick area of less dense land. Land is just less dense crust than ocean crust. Well, because you've got a heavier, thinner crust running into a lighter, thicker crust, well, that thicker, heavier crust is going to get pushed underneath, and as gets pushed underneath, it starts to melt, and it releases volatile chemicals and liquid magma that flow up through the continental crust and form volcanoes. So an example of a continent running into a ocean crust is actually in South America. This is how the Andes are formed in Peru and Chile. Um, the the Pacific crust is running into the South American crust and shoving mountains upward. And that's why we get a lot of earthquakes and a lot of volcanic activity along the Andes. Another option is when two ocean crusts run into each other. Well, they're really heavy and dense, so they're going to push both crusts downward into this oceanic trench. Um, this is where the deepest trenches in the world are formed, where two crusts are being pushed into each other, and eventually one will give and pass underneath the other one, and that will also uh, melt some of the crust and release it as magma, and that's going to create a volcanic arc. Sorry. So an example of this is how Japan and the Philippines were created, because the Filipino plate is getting shoved by the Pacific plate the into the Asian plate, and it releases these volcanic um, all this volcanic activity, which creates islands in the Philippines and Japan. Um, Another option is when you got two continents running into each other. Well, the deeper, thicker part of that continent will get shoved underneath the other continent. But for the most part, the continental crust, the thicker but less dense, the lighter stuff, will get shoved up into wrinkles and folds, and that's how we form the mountains in Nepal and Bhutan, Afghanistan, all of these areas where India is running into China or the Asian plate. Another example of this is in Italy, where in the Alps, where Italy is running into Europe. So in continent to continent collisions, you form mountains, but not a lot of volcanoes. In ocean to ocean crust collisions, you form trenches with a lot of volcanoes. And in ocean to continent crust collisions, you form mountains, but also a lot of volcanoes. So those are the three options. The last option is, well, some of the times crusts aren't going to be moving directly toward each other or directly away from each other. They'll be slipping past each other. So you can think of this as like moving one hand next to the other. Well, there's a lot of friction involved, but you're not going to be opening up huge gaps or creating huge trenches. But we live on top of a really good example of a very large slip boundary in California. So the San Andreas Fault is this giant slip fault here. There's different areas of slip and subduction, or the converging boundaries, different parts of California. But for the most part, um, we just California is one giant plate moving past another giant plate. In the San Francisco earthquake in 1906, this is a picture of what happened. You can actually see where the fence broke and moved. This looks like 4 feet from one place to another. So you can also see this is an example of like less extreme slippage, but you can see this curb is actually cracked, and as time goes by, this will get less and less straight as the as we move inches. So, like scientists have measured the distance that we travel relative to each other, and it's like centimeters every year, or like even millimeters. So very small amounts, less than an inch every year, depending on which fault and the speed of those plates. But it's not very much. So, what evidence do we have to support this theory? Well, quite a bit actually, but we're going to talk about some of them. So, as we track backwards in time, if the continents are moving away from each other now, well, at one point they had to be together in the somewhat recent future when you talk about geology. And you can actually see from the shape of continents that at one point, or the most recent point, they fit together in a somewhat cohesive shape. So South America fits nicely into Africa, North America fits on top of that, Europe and Asia fit in a way on top of that, and then you can shove India, Antarctica, and Australia in down here to show that the shape works this way as well. So um, this wouldn't happen if plates didn't move. So there's no logical reason for the shapes of our continents to match this way if the plates just stood still. Another piece of evidence is the location of fossils. So when they were fit together, plants and animals that could not swim were able to cross from one continent to another. So we should see evidence of fossils that share similarities along these boundaries. And we see a lot of examples. So here are just a few of them. Um, I'm not going to butcher the names, but this guy is found in South America and Africa. This guy is found in Africa, India, and Antarctica. This fern is found in all five of these continents. So there's a lot of examples of fossils that span boundaries in during the time frame of the most recent fitting together. It's not just fossils, but also rock formations and types share boundaries along these lines. So there's a lot of evidence that shows that they fit together like this in the past. Another piece of evidence that we use is the location of volcanoes. So we've already talked about why volcanoes will form at plate boundaries. We'll go into more detail when we talk about volcanoes specifically, but this map showing the location of volcanoes actually tracks really well with the different types of boundaries that we find in different places. So this is a converging boundary layer where the Pacific plate is getting shoved into Asia and the Philippine plate. Philippine plate is getting pushed into Asia. Um, the Pacific plate is forming the Aleutian Islands along Alaska. This is a slip fault. We get some and a subduction fault in different places. So this plate is getting shoved upward, and some of it slips underneath, and we get volcanoes along the edges. So all the places where we see lots of volcanoes is also places where we see evidence of plates moving away from or toward each other or slipping along. So what's going on in Africa here is actually Africa looks like it's splitting into two pieces along a fault line, and in Kenya especially, there's a big rift valley where this plate is moving away from part of Africa, and eventually it'll be a small continent and a much larger one, or a large island, depending on how you classify it. So, yeah. we see evidence about this throughout the world. Well, the location of earthquakes follows a really similar pattern. We can see um, in the diverging sections where we create new crust, a lot of low magnitude earthquakes where new crust is formed. This makes sense because creating new crust would be violent enough to create earthquakes, but it's not going to be as violent as shoving one plate under another. So, where we have converging boundaries, we have these much larger earthquakes and more frequent. As one plate gets shoved underneath another one. So this you get a lot of evidence based on the location of volcanoes and earthquakes. And finally, if scientists are able to calculate the age of rocks based on the radioactive decay of some materials, so they can actually look and see when was this rock formed, because we know when it formed it had this much of this material and now it has this much. Well, the age of rocks, so ocean crust is a little bit different than continental crust. Continental crust is formed in different ways than ocean crust, and it's destroyed by erosion and a lot of different forces. So there's different things to consider there. But if you look at just the ocean crust, well, we can actually see the youngest crust is formed along the center of the ocean where we know that things are diverging, where we have evidence of diverging plates. You can actually look diverging plate boundary all the way through here, through Iceland, where I have that cool picture, along the center of South America and Africa. Remember, these used to fit together, so they're moving away from each other. Also along in the Pacific here. Well, the youngest crust is in those locations. So this is a lot of evidence that all builds to support this idea of plate tectonics. So, to summarize, the surface of the Earth is made up of the solid crust called the lithosphere. This crust is split up into plates. Those plates are moving because the liquid center of the Earth, the magma, is circulating. That circulation causes the force of friction on those plates, and that friction makes the plates move really slowly, really, really slowly, millions and billions of years. So look at this. The oldest ocean crust is 161 million years old. So that's quite old. Continental crust is going to be even older in some places. So millions and millions of years, plates move slowly past each other. And that causes earthquakes, volcanoes, different trenches and mountains in different areas. And all of this combines for a comprehensive picture of how the crust of the earth is formed and the forces involved there. So that's going to be the focus of the next few weeks. We're going to be talking about volcanoes, earthquakes, mountain building, seafloor, and then once mountains are built, how erosion and rivers affect them. And understanding the theory of plate tectonics is key for all the other things that we're going to be talking about from here on out. So, hope you enjoyed it. And that'll be it for today.